Space is often described as empty, a vast, silent nothing stretching between stars and galaxies. No air, no sound, no warmth, just absence. And yet, space has a temperature. That idea alone feels wrong the first time you hear it. Temperature, after all, is something we associate with stuff, with motion, with particles bumping into one another, with breath fogging in winter air or sunlight warming your skin. Temperature feels intimate, local, human. So, how can emptiness be cold? How can nothing have a number? The answer is not just one of physics. It's a story, one that begins long before stars existed, long before planets formed, long before there was anyone to wonder about warmth at all. To understand why space has a temperature and why it matters, we have to let go of what we think empty means. Imagine drifting far from Earth. You leave behind the atmosphere, the whisper of wind, the gentle blanket of air molecules constantly colliding with your skin. At first, sunlight still warms you. Shadows still feel cool. Earth still glows beneath your feet. But keep going, past the moon, past the last traces of Earth's influence, past the comfort of nearby worlds. Eventually, the sun becomes just another bright star in a crowded sky. You turn off your engines. You float. No air touches you. No particles brush past in any meaningful way. By everyday standards, you are surrounded by nothing. And yet, if you carried a thermometer, a perfect one, sensitive beyond any instrument we've ever built, it would not read 0. It would settle very slowly at a temperature just a few degrees above absolute 0. This is the first quiet truth of the universe. Even in the deepest void, space is not perfectly cold, not because something is heating it, but because something ancient never stopped cooling. That something is light. Not the kind of light that illuminates rooms or casts shadows, but a faint, ghostly glow that fills the universe in every direction. Light so stretched by cosmic expansion that it no longer looks like light at all. It looks like temperature. Long before stars ignited, the universe was hot, unimaginably hot. In its earliest moments, everything was packed so tightly that space itself could not exist as we know it. Energy, matter, and radiation were fused into a dense, blinding state, where temperature wasn't measured in degrees, but in impossibly large numbers that defy intuition. As the universe expanded, it cooled, not because heat escaped anywhere. There was nowhere to escape to, but because expansion itself dilutes energy. Picture a fire spreading outward forever. The flames don't vanish, but they grow thinner, weaker, more spread out. The heat doesn't leave. It stretches. The universe did the same. And in doing so, it left behind a thermal fingerprint. That fingerprint is still with us today. It surrounds you right now, even as you read this. It passes through your body, your walls, your planet, unnoticed and unstoppable. It comes equally from every direction, with almost perfect uniformity. It is the afterglow of creation itself, and it sets the baseline temperature of space. This is where the idea of space being cold quietly changes meaning. Space isn't cold because it steals heat like ice. It's cold because it has almost nothing to give back. On Earth, warmth is shared through collisions. air molecules bouncing off your skin, transferring energy. In space, those collisions barely happen. Without contact, heat can only leave you through radiation, and radiation always flows towards something colder. Out there, the coldest thing isn't darkness. It's the universe's background glow, a silent sink for energy. If you were floating in deep space, far from any star, your body would radiate heat away until you approached equilibrium with that background temperature. You wouldn't freeze instantly. There's no icy wind, no sudden shock, just a slow, inevitable cooling. The universe would wait patiently as you surrendered warmth photon by photon. This is not violence, it's balance. And this balance, this cosmic temperature flaw, is not a trivial detail. It shapes everything. It determines how gas clouds collapse into stars. It influences how galaxies form and evolve. It sets limits on how cold matter can become naturally. It defines the ultimate fate of heat itself. Without this background temperature, the universe would behave very differently. Structures might form faster or not at all. Chemistry might stall. Complexity might never emerge. In a very real sense, the temperature of space is part of why we exist. Yet most people never think about it. When we talk about space, we focus on extremes. Black holes, supernovas, infinite distances, blazing stars. We imagine violence and spectacle, but the universe is governed just as much by quiet numbers, by gentle backgrounds, by slow drifts toward equilibrium, by temperatures so low they seem almost philosophical. The strange part is this: the temperature of space is not fixed. It is changing. Right now, as you sit here, the universe is cooling. The background glow is stretching further, thinning out, losing energy. Given enough time, it will approach absolute zero, not by reaching it, but by forever getting closer. An eternal cooling, a cosmic exhale that never quite ends. And that raises questions far larger than physics. What happens to stars when the background temperature drops even lower? What happens to life, to energy, to time itself? What does it mean to live in a universe that is slowly forgetting its own heat? To answer those questions, we need to understand not just that space has a temperature, but why it does, how we discovered it, and how deeply it shapes the story of everything that follows. So let's slow down. Let's listen to the quiet hum beneath the cosmos. And in the next stretch of this journey, we'll trace the origin of that temperature back to the moment the universe first became transparent, when light was finally free to travel and space took on its first measurable chill. There was a time when the universe was too hot to be seen. Not bright, opaque. In those early ages, light could not travel freely. Photons were constantly scattered, absorbed, re-emitted, trapped in a dense fog of charged particles. Space existed, but it was more like the inside of a star than the vast openness we imagine today. Temperature ruled everything. Matter was stripped down to its essentials. Electrons were not bound to atoms. Protons and nuclei floated freely, and radiation dominated the energy budget of the cosmos. The universe wasn't empty. It was crowded, restless, and blindingly energetic. If you had been there, if such a thing were possible, you would not have seen anything at all. Light had nowhere to go. Then, slowly, almost imperceptibly, the universe cooled. Cooling in the universe doesn't happen the way it does in your kitchen. There's no surrounding environment to absorb heat, no colder place for warmth to escape. Instead, cooling happens because the universe expands. As space stretches, radiation stretches with it. Wavelengths grow longer. Energy spreads thinner. Temperature falls, not because energy disappears, but because it becomes more dilute. Over hundreds of thousands of years, this gentle expansion lowered the cosmic temperature enough for something extraordinary to occur. Electrons slowed down, protons waited, and for the first time, atoms could exist. This moment is known as recombination, though the name hides its significance. When electrons finally bound to nuclei, the universe changed state. Neutral atoms formed. And suddenly, light was no longer constantly scattered by free charges. The fog lifted. The universe became transparent. And in that instant, about 380,000 years after the beginning, light was set free. That light still exists. It has been traveling ever since, crossing expanding space, stretching to longer and longer wavelengths, cooling as the universe cools. What began as intense, visible radiation has become something far subtler. Today, it fills the cosmos as a faint microwave glow. This is the cosmic microwave background, the afterimage of the universe becoming visible to itself for the first time. And this glow is why space has a temperature. The cosmic microwave background is not a metaphor. It's not a theory. It's not inferred indirectly. It is measured. In every direction we look, no matter where we point our instruments, we detect the same soft radiation. It comes from no star, no galaxy, no localized source. It comes from everywhere. The universe is bathed in its own memory. If you could see it with your eyes, the sky would glow faintly in microwaves, uniform and calm. No bright spots, no darkness. Just a nearly perfect thermal field, corresponding to a temperature of about 2.7 degrees above absolute zero. That number, 2.7 Kelvin, is the temperature of space. Not because space itself vibrates or holds heat like a material object, but because this ancient radiation defines the lowest energy environment anything can radiate into. It is the coldest ocean anything can swim in. This temperature is not arbitrary. It carries information, tiny variations, differences of just a few millionths of a degree, encode the seeds of galaxies, the density of matter, the geometry of space, and the fate of cosmic expansion. But before it became a precision instrument for cosmology, the cosmic microwave background was simply unexpected. When it was first detected in the 1960 seconds, it wasn't celebrated. It was annoying. Two engineers were working with a sensitive radio antenna, trying to eliminate noise from their measurements. No matter what they did, no matter where they pointed, no matter how carefully they calibrated, they detected a persistent background hiss. It came from everywhere. They checked their equipment, cleaned it, even removed what they believed might be bird droppings inside the antenna. The noise remained. What they had stumbled upon was not interference. It was the universe itself, whispering in microwaves. This discovery confirmed a profound idea. The universe had a hot beginning, and more importantly for our story, it meant that space could never again be truly cold. Because even as stars burn out and galaxies drift apart, this background radiation lingers. It cools, yes, but it never vanishes. Space is haunted by its own past. Think about what that means. When a star shines, it radiates energy outward. When a planet cools, it sheds heat into its surroundings. When a human body rests in darkness, it emits infrared radiation into the night. But all of that radiation has somewhere to go because the universe provides a thermal sink, a baseline temperature that is lower than almost everything else. That baseline is the cosmic microwave background. Without it, heat would have nowhere to flow. This is why the temperature of space matters. It sets the rules for cooling. It determines how fast objects lose heat, how efficiently structures can form, and how low temperatures can realistically go. It shapes the thermodynamics of the cosmos. In a universe with no background radiation, stars might behave differently. Gas clouds might collapse faster, or not at all. The delicate balance between gravity and pressure could shift. The quiet background temperature is not just scenery, it's infrastructure, and it's changing. As the universe expands, the cosmic microwave background continues to cool. In the distant past, it was warmer than starlight. In the far future, it will be colder than almost anything else. This slow cooling defines the arrow of time on a cosmic scale. It tells us where the universe has been and where it is going. But here is the strange twist. Even though space has a temperature, it does not behave like a warm or cold object in the way we instinctively understand. You can't touch space and feel its coldness. You can't insulate yourself from it completely. You can't block it with walls. Because temperature, in this context, is not a substance. It's a condition. To truly grasp what it means for space to have a temperature, we need to rethink how heat actually works, especially when matter is scarce and radiation dominates. We need to understand why astronauts don't freeze instantly, why satellites overheat instead of cooling down, why emptiness can be both brutally cold and dangerously hot at the same time. So next, step away from the early universe and bring the question closer to home. Talk about bodies, heat, radiation, and what really happens when something warm meets the cold of space. There's a common image people carry in their minds. An astronaut drifts too far from their spacecraft. The tether snaps. They float into darkness. Within seconds, the cold of space overwhelms them, freezing them solid, like a forgotten object in a deep freezer. It's dramatic, it's terrifying, and it's wrong. Space is cold, but it doesn't freeze you the way ice does. And understanding why reveals something subtle and important about what temperature really means when matter nearly disappears. On Earth, heat is shared mostly through contact. Air molecules collide with your skin, carrying energy away. Water pulls heat from your body even faster. Touch a cold metal surface, and heat rushes out of you through direct conduction. All of these processes require one thing: particles. Space has almost none. In deep space, there is no air to carry heat away from your body, no surrounding medium to steal warmth through touch. The vacuum is not a refrigerator, it's an insulator. If you were suddenly exposed to space, your body would not instantly freeze. In fact, for a brief time, you might feel almost nothing at all. The real danger wouldn't be cold. It would be pressure loss, oxygen deprivation, boiling bodily fluids. But temperature? Temperature would work slowly. This surprises people because we've learned to associate cold with speed. Cold winds, sudden chills, ice water. But those sensations are caused by efficient heat transfer, not low temperature alone. In space, heat can leave your body only one way, Radiation. Radiation is the quietest form of heat transfer. It doesn't require contact. It doesn't require particles. It doesn't care whether space is empty or full. Everything with a temperature above absolute zero emits electromagnetic radiation. Your body does it right now, glowing faintly in infrared. You don't see it, but it's there. In space, that glow has somewhere to go, into the cold background of the universe. But here's the key point. Radiation is slow compared to conduction or convection. Radiative heat loss is gentle. Even a warm human body takes time to cool by radiation alone. So instead of freezing instantly, you would cool gradually, losing heat photon by photon to the cosmic background. The universe wouldn't rush you. It would wait. This is why spacecraft engineers worry less about freezing and more about overheating. In orbit, satellites and space stations are bathed in sunlight for long periods. With no air to carry heat away, that energy builds up. Electronics can cook themselves if excess heat isn't radiated efficiently. The same emptiness that makes space cold also makes it terrible at cooling things down. This duality confuses us because we're used to thinking of temperature as an aggressive force. But temperature doesn't act. It doesn't reach out and grab heat. Heat moves because of differences, gradients, and because physical mechanisms allow that movement to happen. In space, those mechanisms are limited. So when we say space is cold, what we really mean is this. Space provides a very low temperature environment for radiation to flow into. Not an active freezer. Not a biting cold. Just a vast thermal sink. This matters deeply for how the universe evolves. Stars shine because they can radiate heat into something colder. Gas clouds collapse because they can shed energy. Planets cool and solidify because radiation has a direction to flow. If the background temperature of space were higher, all of this would change. In the early universe, space was warm. Very warm. The cosmic background temperature was thousands of degrees. In that environment, atoms struggled to form. Gas clouds couldn't cool efficiently. Structures grew differently. As space cooled, complexity became possible. Temperature didn't just describe the universe. It enabled it. Even today, the background temperature sets a hard limit. No matter how perfect your insulation, you cannot cool an object below the temperature of the surrounding radiation field without doing work. Absolute zero is unreachable, not just because of engineering challenges, but because the universe itself won't allow it. There is always something warmer than nothing. This is why the phrase cold vacuum of space is misleading. Vacuum isn't cold. It's indifferent. It allows radiation to pass, but it doesn't participate. It doesn't collide. It doesn't comfort or attack. Space doesn't freeze you. You cool yourself into it. And this gentle, one-way loss of heat has consequences far beyond human survival. It defines the lifetime of stars. It controls how galaxies glow. It governs how long structure can resist decay. Eventually, when stars fade and black holes evaporate, radiation will be all that's left, drifting ever colder, ever thinner. The universe is not rushing toward an icy death. It's cooling with infinite patience. When we look at a galaxy, it's tempting to think of gravity as the main architect. Gravity pulls matter together. Gravity sculpts spiral arms. Gravity gathers billions of stars into glowing islands of light. But gravity alone is not enough. If gravity were the only force at work, the universe would look very different, hotter, smoother, and far less structured. The reason galaxies exist in their intricate forms has just as much to do with temperature as it does with mass. Because gravity can pull, but temperature decides whether matter stays. Imagine a vast cloud of gas drifting through space. Hydrogen, helium, trace elements forged in earlier stars. From a distance, it looks like nothing at all, just a faint smudge against the black. Gravity begins its quiet work. The cloud contracts. Particles drift closer together. As they fall inward, something happens. They heat up. This is one of the most important rules of the universe. Compression raises temperature. As gas collapses under gravity, particles move faster. Faster motion means higher temperature, and higher temperature means pressure, an outward push that resists further collapse. This is where temperature becomes a gatekeeper. If the gas can get rid of that heat, gravity wins. If it can't, collapse stalls. So how does a gas cloud cool? Not by touching anything, not by blowing heat away. It cools by radiating. Atoms and molecules emit photons. Energy escapes. Temperature drops. Pressure eases. Gravity pulls tighter. Cooling allows structure. Now here's where the temperature of space enters the story. Radiation only flows when there is a colder place to send it. A gas cloud at 100 Kelvin can radiate efficiently into space at 2.7 Kelvin. The difference is enormous. Energy pours out, but if the background temperature were higher, say tens or hundreds of degrees, cooling would slow dramatically. Gas would struggle to lose heat. Collapse would be inefficient. Stars would form later. Galaxies would grow differently. Some structures might never form at all. In the early universe, this wasn't hypothetical. The cosmic background temperature was once warmer than the surfaces of modern planets. At that time, gas clouds lived in a universe that resisted cooling. Gravity pulled, but heat pushed back. Only when the background temperature dropped below critical thresholds did the universe enter an era where stars could ignite easily. The cooling of space unlocked the night sky. Even today, the background temperature still sets limits. In the coldest regions of space, dark molecular clouds where new stars are born. Temperatures approach just a few degrees above the cosmic background. These clouds are barely warm enough to move, barely energetic enough to resist collapse. They exist on the edge of possibility. Too warm, and they would disperse. Too cold, and chemistry would freeze. Temperature doesn't just affect when stars form, it affects how they form. Hotter gas fragments differently. It tends to form fewer, more massive stars. Cooler gas breaks apart more easily, creating clusters of smaller stars. This subtle shift changes everything downstream. Massive stars live fast and die violently, seeding space with heavy elements. Smaller stars burn slowly, offering stable environments for billions of years. In a warmer universe, long-lived stars like the Sun might be rare, and without long-lived stars, planets, and life become unlikely. The temperature of space also influences the largest structures of all. On scales of hundreds of millions of light-years, matter traces out a vast cosmic web, filaments of galaxies surrounding enormous voids. These patterns emerged because cooling allowed matter to clump rather than smear out evenly. Tiny temperature differences in the early universe were amplified over time, guided by gravity but constrained by thermodynamics. The universe didn't just expand, it cooled into shape, and this shaping continues. As the background temperature drops, cooling becomes easier for smaller and smaller structures in the far future. Objects that cannot cool today may finally be able to shed energy, but there is a limit. Dark energy accelerates expansion, pulling galaxies apart faster than gravity can gather them. Even as space cools, isolation increases. The universe grows colder, but also lonelier. This introduces a quiet irony. Cooling makes structure possible. Expansion destroys connection. The same process that lowers the temperature of space also spreads. Matter so thin that interactions become rare. In the long run, cooling does not mean complexity forever. It means a brief window where structure can exist at all. When we look at galaxies through telescopes, we see light. But what we're really seeing is a history of cooling, of energy finding its way into the vast thermal sink of space. Step by step, photon by photon, galaxies shine because the universe is colder than they are. Stars burn because space waits to receive their light. And that waiting, silent, patient, almost gentle, is what gives time its direction. Right now, the universe is warm, by its own standards. Not warm in any human sense, of course. Space sits just a few degrees above absolute zero. Stars still burn, galaxies still glow, and energy still flows from hot places to cold ones. But this warmth is temporary. The universe is cooling, and it always has been. Not in steps, not in cycles, but in a single, unbroken direction. Every second that passes, space expands. And with that expansion, the background radiation stretches just a little more. Each photon loses a tiny fraction of its energy. The cosmic temperature drops by an amount so small, it's almost meaningless on human timescales. But over billions of years, it adds up. The universe remembers its heat the way embers remember a fire, dimly, fading, unstoppable. There was a time when the background temperature of space was higher than the surface of the sun. Later, it was warmer than boiling water. Later still, warmer than ice. Life, planets, chemistry, all of it emerged during a narrow thermal window in the universe's history. Not too hot, not too cold, just right. This window is closing, very slowly, but inevitably. As the background temperature drops, fewer processes can operate naturally. Chemical reactions slow, cooling becomes easier, but energy sources become rarer. Stars will continue to form for trillions of years, but eventually the raw material will thin out. Gas clouds will fail to collapse. The last stars will ignite in isolation, burning dimly in a darkened cosmos. And then, even they will fade. When stars die, they don't vanish quietly. They leave behind remnants. White dwarfs, neutron stars, black holes, objects that hold enormous amounts of mass but very little warmth. These remnants cool too. White dwarfs glow faintly for billions of years, slowly radiating their heat into space. Neutron stars cool faster at first, then settle into long, quiet declines. Black holes, once thought eternal, also cool. They radiate, infinitesimally, patiently. Even the darkest objects in the universe are not immune to temperature. As time stretches far beyond anything we can intuitively grasp, the universe approaches a state called thermal equilibrium, not because everything becomes equally warm, but because everything becomes equally cold. No gradients, no flows, no work to be done. This is sometimes called the heat death of the universe, but the name is misleading. Nothing dramatic happens. There is no final explosion, no sudden darkness, just a slow settling, a cosmic sigh. In that far future, the temperature of space approaches absolute zero, but never reaches it. The background radiation continues to cool, asymptotically inching closer to nothingness. The universe doesn't end. It quiets. And this is why the temperature of space matters now. Because it defines a clock. Not a clock with numbers or ticking hands, but a thermodynamic one. A measure of how much usable energy remains. A guide to how long complexity can survive. Every thought, every star, every living thing exists because the universe is not yet done cooling. There is something strangely comforting about this. The universe is not rushing us. It is not hostile. It is not impatient. It simply follows the rules. Energy spreads. Temperature falls. Time moves forward. When you step outside on a clear night and feel the cool air on your skin, you are not feeling the temperature of space. Earth's atmosphere shields you from that deeper cold. But beyond the sky, beyond the blue and the black, there is a quieter chill. Not threatening, not sharp, just final. And yet, here we are, living in a universe that still has warmth to spare, still rich with gradients, still capable of stars and stories and thought. The temperature of space tells us not just where the universe is going, but how precious this moment is, because warmth, like light, does not last forever. Measuring the temperature of space sounds impossible at first. You can't scoop up emptiness. You can't place a thermometer into nothing and wait for it to settle. There is no surface to touch, no air to stir, no fluid to expand. And yet, we know the temperature of space with extraordinary precision. Not because we measured space itself, but because we measured what space is filled with. Light. Every object with a temperature emits radiation. The hotter it is, the shorter and more energetic that radiation becomes. Cooler objects emit longer, softer wavelengths. This relationship is so reliable that physicists gave it a name: blackbody radiation. A perfect blackbody emits light in a spectrum that depends only on temperature. No chemistry, no structure, just heat translated into photons. And the universe, remarkably, behaves almost exactly like one. When astronomers first realized that the faint microwave glow filling the sky matched a nearly perfect blackbody curve, something profound clicked into place. This wasn't random radiation. It wasn't leftover starlight. It wasn't noise. It was thermal. The universe itself had a temperature, but detecting that temperature required a kind of listening far subtler than traditional astronomy. Instead of focusing telescopes on stars or galaxies, scientists had to measure a signal that was everywhere at once. No edges, no source, just a uniform background. This required instruments of almost obsessive sensitivity. Detectors cooled to near absolute zero, antennas shielded from Earth's warmth. Satellites launched into space to escape atmospheric interference. To measure the cold of the universe, we had to build things colder than space itself. The first clear measurement was rough by modern standards, but unmistakable. A faint hiss, a smooth spectrum, a temperature just a few degrees above absolute zero. Later missions refined the measurement, mapping the background radiation across the entire sky. What they found was astonishing. Uniformity. In every direction, the temperature was nearly the same, varying by only tiny fractions of a degree. Those variations were so small, they had to be exaggerated by false colors just to be seen. And yet, those tiny fluctuations held the blueprint of everything that would follow. These temperature differences weren't noise. They were structure in its earliest form. Regions slightly warmer or cooler corresponded to tiny density differences in the early universe. Over billions of years, gravity amplified those differences into galaxies, clusters, and vast cosmic filaments. From whispers of temperature came entire worlds. What makes this even more remarkable is how stable the measurement is. No matter where you go in the universe, at least as far as we can observe, the background temperature appears the same. It defines a cosmic rest frame, a reference against which motion itself can be measured. When Earth moves through this radiation, it creates a subtle temperature shift, slightly warmer in the direction of motion, slightly cooler behind. Even our planet leaves a thermal fingerprint on the universe's glow. This tells us something profound about space. The temperature of space is not local, it is global. It does not belong to stars or galaxies. It belongs to the universe as a whole. And because it is global, it is reliable. Engineers designing spacecraft rely on this background temperature when calculating thermal behavior. Cosmologists use it to test models of expansion. Physicists use it to probe the earliest moments of time. It is one of the most precisely measured quantities in all of science, and it comes from almost nothing. There is a strange beauty in that. The coldest thing we know is also one of the most informative. The faintest light carries the deepest memory. The quietest signal tells the loudest story. Space does not shout its temperature, it hums it. But measuring the temperature of space is only half the story. The other half is understanding how that temperature interacts with everything else, how it competes with starlight, how it defines limits for cooling, and how it will eventually dominate when all other sources of heat fade away. To understand that, we need to talk about contrast, about hot and cold sharing the same universe, about why, even in a freezing cosmos, some places still burn bright. So next, we'll explore the tension between stars and space, between blazing furnaces and the cold background that waits patiently to receive their light. The universe is cold. And yet, everywhere you look, there is fire. Stars burn at millions of degrees. Stellar cores crush atoms together with relentless force. Supernovae briefly outshine entire galaxies. Even planets, wrapped in thin skins of atmosphere, hold onto pockets of warmth against the dark. This seems like a contradiction. How can such intense heat exist in a universe whose background temperature barely rises above absolute zero? The answer lies not in opposition, but in imbalance. Heat does not require a warm universe to exist. It requires gradients, differences. As long as there are places much hotter than their surroundings, energy can flow. And as long as energy flows, structure can persist. The universe does not demand uniformity right away. It allows exceptions. Stars are those exceptions. They are born when gravity gathers gas tightly enough that temperature rises faster than energy can escape. In stellar cores, the balance tips, pressure and heat become extreme. Nuclear fusion ignites. Once that happens, stars become engines, converting mass into energy and pouring it into space. They shine because space is colder than they are. They live because the universe gives them somewhere to lose heat. This relationship is asymmetric. Stars burn quickly by cosmic standards because the background temperature is so low. The larger the difference between a star's surface temperature and the surrounding space, the faster it can radiate energy. A star in a warmer universe would cool more slowly. In our universe, stars blaze themselves into exhaustion. The same principle applies to planets. Earth stays warm, not because space is cold, but because the sun is hot. Solar energy arrives faster than Earth can radiate it away, at least for now. At night, when the sun's input stops, Earth radiates its heat back into space. The planet cools. Morning comes, the cycle repeats. The cosmic background doesn't actively cool Earth. It simply accepts what Earth gives up. This acceptance is what makes atmospheres possible. If space were warmer, planets would struggle to shed excess heat. Atmospheric circulation would change. Climate stability would be harder to maintain. The quiet cold beyond our skies is part of what keeps Earth habitable. There's a deeper lesson here. Temperature does not enforce sameness. It enforces direction. Energy flows from hot to cold, always, without exception. That simple rule shapes everything from boiling water to the lifespan of galaxies. The coldness of space is the ultimate destination for all energy in the universe. Every photon, eventually, joins the background. This is why starlight matters. When you see a star, you are watching energy on a one-way journey. That light will never return to the star. It will scatter, stretch, cool, and fade into the cosmic background. Stars are temporary precisely because space is cold. They exist to burn themselves out. And yet, that burning creates opportunity. Heavy elements forged in stellar cores, planets assembled from stellar debris, chemistry sparked by gradients of energy and temperature. Life itself is an exploitation of imbalance. We exist because the universe is not in equilibrium, but equilibrium is the destination. As stars fade, as galaxies drift apart, as black holes evaporate, fewer and fewer sources of concentrated heat remain. The background temperature continues to fall, but it also becomes dominant in the far future. The universe will still have temperature, but almost no contrast. Cold everywhere. Until then, we live in a universe of fire set against ice. A universe where the cold of space does not smother heat, but gives it meaning. Between galaxies lies a kind of darkness we rarely talk about. Not the dramatic darkness of a starless night, but something quieter, emptier, more complete. These regions are called cosmic voids, vast expanses where galaxies are scarce, matter is thin, and distances stretch for hundreds of millions of light years. If space feels empty near a star, these places feel almost unreal. And yet, even here, temperature still exists. At first glance, voids seem like the coldest places imaginable. There are few stars to heat them, almost no gas to collide, nothing to stir energy around. But temperature, once again, refuses to disappear. The intergalactic medium, the thin gas that drifts between galaxies, is incredibly sparse. In many regions, there may be only a few atoms per cubic meter, less than what we would call a vacuum on Earth. These atoms move slowly. Their kinetic energy is low. By most definitions, they are cold. But they are not colder than space itself. They cannot be. No matter how isolated a particle becomes, it still sits inside the same cosmic radiation field. It still absorbs and emits photons from the background. It still participates, however faintly, in the universe's thermal balance. Even in the deepest void, the background temperature sets the floor. This is what makes cosmic cold so strange. There is no such thing as below space. In fact, some voids are warmer than you might expect, not because of stars, but because of history. When galaxies formed, they heated their surroundings. Supernovae and active galactic cores blasted energy outward, sending shockwaves into the intergalactic medium. Those waves traveled far, sometimes into regions that now appear empty. The heat remains. Sparse gas cools very slowly. With so few particles to radiate energy, the process can take billions of years. Some of the emptiest regions of the universe are still cooling from ancient events. So temperature in voids is a record, a memory of violence long past, a whisper of galaxies that once flared nearby. This challenges another intuition we carry. We tend to think of emptiness as timeless, as static, as a place where nothing happens. But voids evolve. They expand. They cool. They remember. The temperature of empty space changes not because something is happening now, but because something happened once. And this matters. Void temperatures affect how matter drifts, how gas accretes onto galaxies, how large-scale structure grows. Even tiny thermal pressures, when applied over enormous distances and timescales, can redirect the flow of matter on cosmic scales. Small numbers rule. There's also something deeply poetic here. The coldest places in the universe are not dead. They are quiet. They hold echoes. They wait. As the universe ages, voids will grow larger and colder. Galaxies will move farther apart. Interactions will become rare. Eventually, many regions of space will never again be warmed by starlight. They will live only by the background glow. And yet, even then, temperature will still exist. A number, a condition, a limit. Space will never be truly empty of heat. This brings us to a subtle but important realization. Temperature does not require complexity. It doesn't need atoms in bulk. It doesn't need stars or planets. It doesn't even need matter. All it needs is radiation. As long as light exists, temperature exists, and light, once created, is stubborn. It travels, it stretches, it cools, but it does not vanish. There is a number that haunts physics. 0 Kelvin. Absolute zero. The point where all thermal motion, every vibration, every jitter of particles comes to a stop. It is often described as the coldest temperature possible, and yet the universe will never reach it. Not because it doesn't have enough time, not because something stops it, but because absolute zero is not a destination. It's a limit. In everyday life, cooling feels straightforward. You remove heat, temperature drops. Remove more heat, it drops further. Put something in a freezer, then in liquid nitrogen, then in ever colder environments, and it keeps approaching zero. but it never arrives. No matter how clever the method, no matter how patient the experiment, there is always a remainder, a final bit of motion that refuses to disappear. This isn't a technical problem, it's a rule. The universe obeys the same rule. As space expands, the background radiation cools. Its temperature decreases smoothly, predictably, endlessly, but it never reaches absolute zero. Why? Because reaching zero would require time to stop. Temperature, at its deepest level, is tied to motion. Not just motion of particles, but motion encoded in fields, fluctuations, and quantum uncertainty. Even in a perfect vacuum, even at the lowest conceivable energy state, there is still activity. 0-point energy. Quantum fluctuations. The restless hum beneath emptiness. The universe cannot turn itself completely still. This means the future of cosmic temperature is asymptotic, always approaching, never arriving. The background radiation will grow colder and colder. Its photons stretch to wavelengths longer than galaxies, longer than clusters, longer than anything with structure. Eventually, that radiation will be so dilute that it becomes functionally undetectable, but it will still exist. In that far future, asking what is the temperature of space becomes almost philosophical. The number will be unimaginably small, fractions upon fractions of a degree above zero, a temperature so low that no natural process can notice it. And yet, it will still matter, because even then, it sets a boundary. There is a quiet elegance to this. The universe began hot and dense. It expands, cools, simplifies. It never quite finishes. There is no final state where nothing happens, just slower and slower change. This has implications not just for physics, but for meaning. The universe does not end in a snap. It does not collapse into silence. It fades, gracefully, endlessly. And here is the remarkable part. The same temperature rules that govern the end of time also govern your body right now. You stay alive because your internal processes operate far from equilibrium. You eat, you move, you radiate heat into cooler surroundings. You exist because the universe is not done cooling. Every living system is a small rebellion against equilibrium, a temporary island of warmth in a cold sea. And space, the vast, patient cold, makes that rebellion possible. This reframes the idea of cosmic cold. It is not an enemy. It is not a threat. It is a condition that allows contrast, direction, and time. Without cold, there is no flow. Without flow, there is no change. Without change, there is no story. The temperature of space is not just a number scientists measure. It is the background against which everything meaningful happens, including this moment. When humans first imagined traveling into space, they worried about freezing. It seemed obvious. Cold space. Fragile machines. Inevitable ice. But the first spacecraft taught us a counterintuitive lesson. Cold was rarely the enemy. Heat was in space. Machines don't struggle to stay warm. They struggle to get rid of warmth. Every electronic component produces heat. Every processor, battery, and power system leaks energy as it works. On Earth, air carries that heat away. Fans blow, fluids circulate. Heat disappears into the environment. In space, none of that works. There is no air to move, no fluid to convect, no medium to help. A spacecraft can only cool itself by radiating energy away, slowly, patiently, into the cold background of the universe. This is where the temperature of space becomes practical. Engineers must design spacecraft as if they are constantly negotiating with the cosmos. Every surface, every material, every angle matters. Too much radiation outward, and parts freeze in shadow. Too little, and systems overheat in sunlight. Thermal balance becomes an art. Consider a satellite in orbit. As it circles Earth, it passes in and out of sunlight. One side bakes, the other freezes. Temperatures can swing hundreds of degrees in minutes. The background temperature of space never changes, but exposure does. To survive, spacecraft wear thermal blankets, reflective coatings, and radiators carefully tuned to emit heat at just the right rate. They are wrapped, not to stay warm, but to stay stable. Some missions take this balancing act to extremes. Certain space telescopes must be colder than almost anything naturally occurring in the universe. Their instruments are designed to detect faint infrared signals, whispers of heat from distant stars and galaxies. Any warmth from the telescope itself would drown out the signal. So engineers shade them from the sun, Earth, and even the moon. They let the telescope radiate its heat into deep space until it approaches the background temperature, not zero, never zero, but cold enough to listen. This is another quiet truth. The temperature of space is not just an abstract cosmic fact. It is a tool, a resource, a natural refrigerator that, when used carefully, allows us to see farther back in time than any other method. Yet even here, the universe sets limits. No spacecraft can cool itself below the background radiation without expending energy. No matter how perfect the design, the cosmic temperature remains the flaw. The universe always has the last word. This interplay between machine and cosmos mirrors the relationship between life and space. Both must fight entropy locally while surrendering to it globally. Both survive by managing energy gradients, not by eliminating them. In this way, spacecraft are not invaders in space. They are participants. And as we push farther, sending probes into interstellar space, beyond the influence of the sun, the temperature of space becomes the dominant environment. There is no shelter, no planetary warmth, just the slow, steady exchange of radiation with the universe itself. Out there, machines become quiet, power dwindles, heaters cycle less often, instruments rest between observations. Eventually, even the most carefully designed spacecraft will cool, drift, and fall silent, becoming just another object, surrendering its heat to the cosmic background. This is not failure, it is completion. Every machine we send into space is a temporary disturbance in a long cooling process. For a while, it glows, electrically, thermally, meaningfully. Then it fades. There is a strange disconnect between knowledge and sensation. We know space has a temperature. We can measure it. We can calculate its effects. And yet, when we imagine floating in space, we don't imagine feeling cold. We imagine nothing. No touch, no pressure, no sensation at all. That intuition is closer to the truth than it first appears. Cold, as humans experience it, is not a direct perception of temperature. It is a story told by nerves. On Earth, when you feel cold, what you're actually sensing is heat leaving your body. Air molecules carry energy away. Water does it faster. Metal faster still. Your nerves interpret rapid heat loss as cold in space. That mechanism vanishes. With no air to brush your skin, no fluid to steal warmth, there is no immediate signal to your nervous system. Heat leaves you slowly, silently, through radiation. Your body does not register that as cold, at least, not at first. This is why the vacuum of space feels so deceptive in thought experiments. There is no bite, no sting, no instant feedback. The danger is not sensation, it's time. This makes the temperature of space feel unreal. How can something be cold if you can't feel it? The answer is that temperature is not a force. It does not act upon you unless there is a pathway. In space, most of those pathways are gone. This teaches us something subtle about reality. Many of the properties we associate with the world, hot, cold, loud, soft, are not intrinsic. They emerge from interaction. Without interaction, the universe is quiet. The cosmic background radiation does not push against you. It does not announce itself. It simply exists, passing through you, interacting weakly with your atoms. You are immersed in a thermal field you cannot sense. Right now, even on Earth, the background radiation is here. It flows through walls, through bodies, through planets. We live inside the universe's temperature. We just don't notice. This invisibility has consequences. It means the most important influences on the cosmos are often the quietest ones, the things that don't announce themselves with light or sound. Temperature shapes the universe without being felt, and this is why the story of space's temperature is not about drama. It's about patience, about slow change, about systems gently drifting toward balance. In human history, we've learned to respect violent forces, storms, earthquakes, fire. But the universe is ruled by gentler laws: expansion, cooling, entropy. They don't strike. They accumulate. The cold of space is not something that attacks. It is something that waits. And in waiting, it defines the direction of everything else. When we talk about the future of the universe, we often focus on spectacular endings: collapsing stars, exploding galaxies, black holes swallowing light. But the dominant story is quieter: a long fade, a steady loss of contrast, a universe that becomes less interesting, not because anything breaks, but because nothing changes anymore. Yet for now, change still happens. Temperature differences still exist. Energy still flows. Stories still unfold, including this one. There is something almost absurd about it. A single number, a few digits, a temperature barely above absolute zero. And yet, that number quietly threads through everything we've talked about: the birth of stars, the growth of galaxies, the fate of machines, the direction of time itself. The temperature of space is not dramatic, but it is decisive. We tend to look for meaning in extremes, in the hottest stars, in the most massive black holes, in the most violent explosions. But the universe is not ruled by its loudest moments. It is ruled by its background conditions, the things that never go away. The cosmic temperature sets the stage. It doesn't write the script. It doesn't choose the characters, but it determines what kinds of stories are even possible. Too warm, and structure dissolves. too cold, and change slows to nothing. We exist in a narrow thermal corridor, one that is slowly closing. This reframes how we think about scale. When you feel small under a night sky, it's not just the size of the universe that overwhelms you, it's the time scale. The universe has been cooling for nearly 14 billion years, and it will continue to cool for trillions more. Compared to that process, civilizations flicker like sparks, and yet those sparks matter because they exist at all. The temperature of space reminds us that the universe is not static. Even when nothing seems to be happening, something is always changing. Radiation stretches, energy thins, time advances silently. This also changes how we think about emptiness. Space is not a void waiting to be filled. It is an environment. It has conditions, constraints, rules, and one of those rules is temperature. When astronomers point their instruments into darkness and find meaning there, they are not extracting secrets from nothing. They are listening to the universe's most persistent signal, the one that has been there since the beginning. There is a quiet humility in that. The universe does not hide its deepest truths in complexity. It hides them in simplicity. A smooth glow, a nearly uniform temperature, a gentle decline. And perhaps that's why this story matters. Not because it tells us how cold space is, but because it shows us how much can arise from something so minimal, from a faint afterglow, from a few degrees of warmth, from imbalance. It's easy to think of the temperature of space as something out there, beyond the atmosphere, beyond the moon, beyond the reach of everyday life. But the truth is quieter and stranger. You live inside it. Right now, as you sit reading these words, the cosmic background radiation is passing through your body. It does not stop at your skin. It does not notice your bones. It does not care that you are warm, alive, thinking. It simply flows. Every second, trillions of ancient photons, older than Earth, older than the sun, slip through you, stretched thin by billions of years of expansion. They carry the temperature of the universe with them, and you don't feel a thing. This is what it means to live inside a background. Not to be affected dramatically, not to be pushed or pulled, but to be contextualized. Your warmth only makes sense because something colder exists. Your metabolism only works because energy can flow outward. Your thoughts require gradients, differences between inside and outside, before and after. The temperature of space is the silent partner in every living process. On Earth, we are protected from that deep cold. The atmosphere traps heat. The sun replenishes energy. The planet cycles warmth through oceans and winds and seasons. Earth is a bubble of defiance, a temporary one. But even here, the background waits. Every night, Earth radiates heat away. Infrared photons leave the surface and escape upward, passing through the atmosphere, heading into space. They do not come back. They join the universe's slow cooling. Earth stays warm only because the sun pays the energy bill. This perspective changes how we see night. The darkness above you is not empty. It is receptive. It is where Earth sends its excess warmth. It is where the planet exhales. The sky is not just something you look at. It is something you interact with. The same is true for every warm thing. Cities glow in infrared. Animals shed heat. Your body leaks warmth constantly. All of it flows outward, ultimately joining the background radiation that defines the temperature of space. Nothing keeps its heat forever. This is not loss in a tragic sense. It is circulation. The universe is not a hoarder of energy. It is a distributor. Energy begins concentrated, inside stars, inside fusion reactions, inside living cells, and ends diffuse, spread thin across expanding space. Temperature tracks that journey. Seen this way, the cosmic background is not just a remnant of the past, it is the destination. Every fire eventually becomes part of it. Every glow fades into it. Every story releases its warmth there. And yet, that doesn't make warmth meaningless. Quite the opposite. It makes it precious, because warmth is temporary by design. If the universe did not cool, nothing would change. If space were not cold, nothing could radiate. If temperature were uniform, time would lose direction. The universe would be eternal and inert. Instead, we live in a universe that allows moments. Moments of heat, moments of light, moments of awareness, moments like this one. Understanding the temperature of space doesn't make the universe feel colder. It makes it feel more intimate. It reminds us that we are not separate from the cosmos. We are immersed in it, participating in its slow evolution, whether we notice or not. There is a difference between living inside something and knowing you live inside it. For most of human history, the temperature of space was irrelevant. People felt heat and cold locally, sun on skin, wind on face, fire in the dark. The sky was distant, symbolic, unreachable. Cold was something that came with winter. Heat was something you could build or escape. The universe itself felt timeless. Then we learned otherwise. We learned that the sky has a temperature, that it is changing, that it has been cooling for billions of years, and will continue to do so long after we are gone. And once you know that, it quietly alters how everything feels. Because a cooling universe is a universe with a direction. Not morally, not emotionally, but physically. There is a before and an after written into the laws themselves. Energy spreads. Contrast fades. Complexity has a window. This knowledge doesn't shout. It doesn't demand action. It simply sits with you, like the awareness of aging, like the sound of a clock in a quiet room. Most of the time, it changes nothing about your day. You still eat, you still sleep, you still worry about small things, and yet, somewhere in the background, just like the cosmic temperature itself, there is an understanding that everything you do happens inside a larger drift. Nothing is static. Nothing is permanent. For some people, this thought is unsettling. A universe cooling toward darkness. A future with fewer stars. An end to warmth. It can feel like meaning draining away. But that reaction comes from a misunderstanding. Meaning does not require permanence. In fact, permanence often destroys meaning. If nothing could end, nothing would matter. The temperature of space tells us that the universe values process over stasis. Things happen because they cannot last. Stars shine because they will burn out. Life exists because energy gradients are temporary. Thought emerges because equilibrium has not yet arrived. A cooling universe is not a dying one. It is a universe that makes room for stories. Think of a campfire. Its warmth matters precisely because it will fade. People gather closer. speak softly, share moments, because the fire will not last all night. The universe is like that. A very slow fire, a very long evening, and we are alive during the warm part. Not the hottest, not the coldest, but the part where complexity is still possible. Knowing this does not make the present fragile. It makes it rare. When astronomers measure the temperature of space, they are not just collecting data. They are placing us in time. They are saying, you are here, not just in space, but in the universe's thermal history, born after the fireball, living before the fade. This perspective doesn't shrink human experience. It enlarges it. Your warmth is not trivial. Your energy is not wasted. Your existence is part of the universe's long cooling story. Even your thoughts release heat. Neurons fire. Energy moves. Photons eventually escape your body. One day, that energy will be part of the background too. Not lost, just spread. And that is the quiet promise hidden inside the temperature of space. Nothing vanishes. Everything diffuses. There is a kind of comfort that comes from slowness. Not the forced slowness of waiting in line or watching a clock crawl forward, but the natural slowness of things that are not in a hurry to become anything else. The universe is like that. It is not rushing toward its future. It is not anxious about its cooling. It does not resist the direction it's moving in. It simply continues. Once you understand that space has a temperature and that this temperature is slowly falling, something subtle shifts. The universe feels less chaotic, less aggressive, less unpredictable. Not because nothing bad can happen, but because everything follows a deep, steady rhythm. Explosions still occur. Stars still die violently. Galaxies still collide, but these events are surface ripples. Beneath them is a calm current. Expansion, cooling, diffusion. The long story. This is why astronomers can speak calmly about cosmic futures measured in trillions of years. Not because they are detached from drama, but because they see how small drama is compared to drift. The universe does not lurch. It glides. When people imagine the end of the universe, they often imagine darkness as something sudden and frightening. But cosmic darkness is not a blackout. It is a dimming, so slow that no one thing ever notices it happening. The temperature of space drops by tiny fractions over immense spans of time. If you lived for 1 billion years, you would still barely perceive the change. And yet, over enough time, everything changes. This is not violence. It is patience. There is something deeply human in finding reassurance here. Our own lives are brief and fragile. We experience change as loss because it happens faster than we can adapt. The universe teaches us another scale of change, one where endings are not abrupt, but gradual, almost gentle. In a cooling universe, nothing is taken away suddenly. Heat fades, light stretches, motion slows. Everything is given time. This doesn't make loss easier on a personal level, but it places loss inside a larger kindness. A universe that allows things to end slowly is a universe that allows them to be fully while they last. When you think about space as cold, it's easy to imagine it as hostile. But perhaps cold is the wrong emotional word. Space is not cruel, it is neutral. And neutrality, on cosmic scales, can feel like mercy. The background temperature does not judge what radiates into it: a star, a planet, a human body. All are received the same way. All are allowed to cool at their own pace. This is why the idea of space having a temperature matters beyond science. It reframes silence. It reframes emptiness. It reframes rest. To rest is not to stop existing. It is to stop resisting change. The universe rests by cooling. And maybe that's why this story has slowly shifted its tone from explanation to reflection to calm, because understanding the temperature of space isn't meant to excite you, it's meant to settle you. Night feels natural to us, not dramatic, not alarming, just expected. The sun sets, light fades, the world cools, sounds soften, the body slows. We rarely stop to consider that night is not just a local event. It is a small reflection of something much larger. Night happens because Earth turns away from the sun. But the reason night feels the way it does, the cooling, the quiet, the sense of settling, comes from space itself. From the fact that beyond our atmosphere, there is a colder place for heat to go. As evening arrives, the ground releases warmth upward. Trees, buildings, oceans, all of them radiate energy into the sky. You can't see it, but it's happening constantly. The planet exhales, and space receives it. This exchange is gentle. No wind pulls the heat away. No force demands it. The warmth simply leaves because it can, because the universe allows it to. This is why nights are often calm. The chaos of daytime is powered by incoming energy. Sunlight, driving winds, storms, movement, activity. When that input stops, the system relaxes. Energy drains outward. Temperature falls. Order softens. Seen this way, night is a collaboration between Earth and the cosmos, a shared rhythm, a reminder that even planets need rest. When you lie awake at night and feel the air cooling around you, you are participating in a process that extends far beyond your room, your city, your world. Your warmth, too, is leaving, slowly, quietly, radiating upward, outward, into the same cold background that waits for everything. This is not loss, it is balance. The universe does not demand that things stay warm. It only asks that they share. That sharing is what makes sleep possible. Your body lowers its temperature slightly when you rest. Metabolism slows, energy use becomes more efficient, consciousness loosens its grip. You cool to sleep. In a universe that never cooled, rest would be impossible. There would be no contrast between day and night, no release of tension, no rhythm of waking and letting go. The cosmic temperature gives us permission to stop, to dim the lights, to drift. This is why stargazing often makes people feel calm. The stars are bright, yes, but the space between them is darker, larger, more dominant. Your eyes adjust, your thoughts slow, the background takes over. The universe at night does not feel empty. It feels spacious. And space, when it is not demanding anything from you, can feel like relief. As the universe ages, night will grow longer. Stars will be fewer. Background light will dim further. Cooling will deepen. But the quality of night, the quiet, the stillness, will remain. Night is not a phase, it is a direction. And every time you fall asleep, you move a tiny step in that direction too, not toward nothingness, but toward rest. At some point, understanding becomes unnecessary, not because there is nothing left to learn, but because learning has done its work. The mind no longer needs to hold the universe tightly. It doesn't need to analyze or measure or explain. It can float. Think about how drifting feels in water. When you stop kicking, stop reaching, stop trying to stay upright, something gentle happens. The water holds you. Movement slows. Breathing finds its own rhythm. You are still awake, still aware, but effort fades. This is what the universe offers when you stop resisting it. Not answers, not revelations, just support. The temperature of space is part of that support. It is low enough to accept heat, stable enough to be predictable, quiet enough to not demand attention. It does not fluctuate wildly. It does not surprise you. It just is. So much of anxiety comes from unpredictability, from systems that change suddenly, from forces that push without warning. The universe, on its largest scales, does not behave that way. It is slow, incredibly slow. Expansion happens too gently to feel. Cooling happens too gradually to notice. Time stretches until urgency loses meaning. When you let that scale enter your thoughts, something loosens. Your worries do not disappear, but they shrink. They become localized weather inside a much larger climate. The cosmic background radiation does not care what you are thinking. And somehow, that can feel comforting. There is no judgment in it, no expectation, just a steady presence. Everything that radiates into space is treated the same. Joy, pain, light, heat, all diffuse. All are allowed to spread out thinly, evenly, without resistance. This means nothing is trapped. Not energy, not moments, not you. When people talk about letting go, they often imagine loss. But letting go can also mean trust. Trusting that what leaves you is not destroyed. It simply changes form. It becomes part of something wider. The universe has been practicing this for billions of years. Stars let go of light. Galaxies let go of heat. Space receives it all. And in receiving, space remains calm. It does not fill up. It does not overflow. Because expansion creates room. Always more room. This is perhaps the deepest comfort of all. No matter how much energy is released, no matter how many stories unfold, the universe has space for them. It is never crowded. As you lie still, whether physically or just in thought, you are doing something very similar to what the universe itself does. You are allowing motion to slow, allowing warmth to spread, allowing time to pass without interference. Nothing needs to be achieved here. There is no destination, just continuation. There is a rare kind of peace that comes when nothing is required. No decisions, no reactions, no explanations, just presence. The universe, in its largest sense, asks nothing of you. It does not need you to understand it. It does not need you to keep up. It does not hurry you along. It expands whether you watch or not. It cools whether you think about it or not. You are allowed to be still inside it. This is easy to forget in a world that constantly asks for attention. Messages arrive, tasks stack up, time feels tight. But beyond all of that, far beyond the scale of hours and days, there is a backdrop that never rushes. The temperature of space does not spike. It does not fluctuate with emotion. It does not respond to urgency. It remains. Imagine removing yourself from effort for a moment. Not solving, not planning, not remembering, just breathing. This is closer to how the universe operates than we often realize. It does not strive. It does not optimize. It simply follows its nature. Cooling is not a goal. It is a consequence. And consequences, when they are gentle and consistent, can feel like guidance. Everything in the universe eventually releases what it holds. Stars release light. Planets release heat. Even black holes, over unimaginable spans of time, let go. Nothing is forced. Nothing is ripped away. Release happens because there is space to receive it. That receiving space is what we call cold. But cold here is not absence. It is openness. To be cold, in the cosmic sense, is to be available. Available to accept energy. Available to absorb change. Available to allow things to move on. This is why the cold of space is not sharp. It is not hostile. It is patient. When you stop trying to hold everything together, you are doing something very old, very universal. You are letting gradients flatten, letting tension ease, letting energy find its way outward. Sleep works the same way. You don't force yourself to sleep. You allow it. You dim lights, lower stimulation, reduce effort, and sleep arrives when resistance fades. The universe does not sleep, but it does rest in its own way, through cooling, through spreading, through quiet continuation. There is nothing dramatic about this rest. No signal announces it. It is simply always happening. And the longer you sit with that idea, the less you feel the need to add anything to it. No conclusions, no lessons. Just the sense that being part of such a universe is not a burden, it is a permission. There is a pace slower than walking, slower than breathing, slower than waiting. It is the pace of the universe itself. Nothing in the cosmos is in a hurry. Even the fastest things, light, particles, explosions, exist inside a framework that changes almost imperceptibly. Expansion happens beneath everything else. Cooling happens beneath even that. A process so slow, it feels like stillness. When you match that pace, something inside you adjusts. Thoughts stop stacking. Urgency loosens. Time feels wider. The temperature of space changes so slowly that it barely feels like change at all. 1,000,000 years pass. 1,000,000,000, and the universe is only slightly cooler than before. There is no rush toward cold, only direction. This is why the future of the universe is not frightening when you truly imagine it. Fear requires suddenness. Fear requires surprise. The universe offers neither. Instead, it offers gradual fading. Stars burn out one by one. Galaxies drift apart. Light stretches until it blends into the background. Nothing collapses all at once. Nothing is taken away abruptly, and because of that, nothing is demanded of you. You do not need to prepare. You do not need to solve anything. You do not need to keep up. Your life unfolds on a scale that the universe easily accommodates. Every moment you experience fits comfortably inside cosmic time. There is room for mistakes, room for pauses, room for rest. The cold of space does not rush to claim warmth. It waits. And waiting, on cosmic scales, is indistinguishable from kindness. As you let this pace sink in, you may notice your own slowing. Muscles loosen, breathing deepens, attention drifts outward instead of inward. This is not emptiness, it is spaciousness. The universe does not fill every moment with activity. Most of it is quiet, most of it is dark, most of it is cool. And that is not a flaw. It is what makes the bright, warm moments stand out. Without long stretches of cold, heat would be meaningless. Without silence, sound would blur. Without night, day would exhaust itself. The universe understands balance intuitively, not by planning, but by unfolding. There is no deadline written into the universe. No countdown. No final warning. No moment where everything suddenly must be finished. The universe expands. The universe cools. And it does so without expectation. This is easy to forget, especially when life feels urgent. Clocks ring, schedules tighten, days feel too small for everything they must contain. But none of that urgency exists beyond us. Space does not hurry heat away. It does not pull energy faster than it must. It does not demand progress. It simply allows things to move when they are ready. Even cooling, something we often associate with loss, happens gently. A photon leaves a star. It travels for millions, billions of years. Its wavelength stretches slowly, patiently. There is no shock at the end of its journey, just diffusion. The temperature of space reflects this attitude: low, stable, unconcerned. It is not trying to become colder quickly. It is not trying to reach an end. It is just continuing. When you hold that idea for a moment, something subtle shifts. You realize that urgency is local. It belongs to organisms with short lives, to minds that measure time in hours, to hearts that fear running out. The universe does not share that fear, and because it doesn't, you don't have to either. Not all the time. You are allowed to slow down inside something so patient. You are allowed to take a breath without using it for anything else. You are allowed to rest without justification. The cold of space is not a pressure. It does not push. It does not pull. It simply is there, ready to receive whatever warmth is released, whenever that release happens. This is why nothing in the universe is truly wasted. Energy does not disappear. Moments do not vanish. They spread. They thin. They become part of a wider field. When you stop rushing, you begin to feel that widening. Thoughts stretch farther apart. Silence grows more comfortable. Time feels less like a container and more like an open horizon. The universe has been doing this for nearly 14 billion years. It has never needed to speed up. There is space between stars, and there is space between thoughts. Most of the time, we rush past both. Thoughts arrive quickly. One follows another. They overlap, stack, compete. But if you pause just slightly, you begin to notice the gaps, moments where nothing is being said inside your head. Those gaps are not empty. They are spacious. The universe is mostly like that. Not events, not objects, but space between them, between galaxies, between photons, between moments. The temperature of space lives in those gaps, not attached to anything solid, not concentrated, just present. When physicists talk about the cosmic background temperature, they are describing something that does not announce itself. It doesn't flicker. It doesn't pulse. It doesn't demand attention. It is simply there, everywhere, evenly, like silence in a quiet room. Silence is not the absence of sound. It is the absence of demand. When you sit long enough without reaching for the next thought, the mind begins to behave more like the universe. Less grasping, less urgency, more room. This is not emptiness. It is relief. Heat flows because there is space to receive it. Thoughts settle because there is space to hold them. Without space, nothing can move. The cold of space is what gives the universe room. Room to cool, room to expand, room to continue without friction. You are allowed that same room right now. You do not need to fill this moment with meaning. You do not need to extract a lesson. You can simply notice that nothing is required. The universe does not fill itself completely. Most of it is open. Most of it is quiet. Most of it is patient. And that patience extends to you as you rest here. Between ideas, between sentences, time does not stop, but it loosens. It becomes less sharp, less insistent. This is what cooling feels like on the inside. Not freezing, not shutting down, just softening. At some point, the foreground fades. Details lose their sharp edges. Concerns stop insisting. The background becomes enough. This is how the universe prefers to be seen. Not as a collection of dramatic objects, but as a continuous field, smooth, wide, unbroken. Stars are accents. Galaxies are ornaments. The real presence is the space that holds them. The background, the temperature of space, belongs to that background. It does not spike. It does not fluctuate wildly. It does not call attention to itself. It is steady, and steadiness has a way of calming whatever is placed inside it. When you stop focusing on individual thoughts, something similar happens inside you. The background of awareness becomes noticeable, a gentle hum, a quiet continuity. Thoughts still appear, but they pass through a larger stillness. This is not emptiness. It is support. The universe supports everything by doing almost nothing, by being cold enough to receive heat, by being vast enough to receive motion, by being patient enough to receive time. Nothing needs to be pushed away. Nothing needs to be held tightly. The background takes care of it. This is why the idea of a cosmic temperature can feel oddly reassuring. It tells you that there is a baseline beneath all experience. Something stable, something reliable. Even when stars explode, the background remains. Even when galaxies collide, the background remains. Even when thoughts surge and emotions rise, There is still something underneath that does not change quickly. You can rest there. The universe has been resting there for billions of years, cooling slowly, expanding gently, holding everything without strain. If you imagine drifting farther and farther from all sources of light, past stars, past galaxies, into the wide spaces between clusters, you would not encounter chaos. You would encounter quiet, a faint glow, a uniform temperature, a sense that nothing is being demanded of you. That same quiet exists inside you when effort relaxes. You don't need to create it. You only need to stop filling the space. Time usually feels sharp. Minutes cut into hours. Deadlines press forward. Moments feel like things you can miss. But that sharpness belongs to small scales, to lives measured in decades, to bodies that need rhythms, to minds that count. The universe does not experience time that way. For the universe, time has no edges. It does not begin sharply in the present. It does not end abruptly in the future. It simply extends. Cooling happens inside that extension, not as an event, but as a condition. The temperature of space does not drop in the way a thermometer falls in winter. There is no sudden shift you could point to and say, "Here, now it is colder." It just becomes. This is what it means for something to be asymptotic. Always approaching, never arriving, always continuing, never finishing. Human minds are uncomfortable with that idea. We like endings. We like conclusions. We like moments where something becomes complete. The universe offers none of that. Instead, it offers duration. A long, smooth continuation where changes are so gentle they blur into stillness. When you lie awake at night and lose track of time, you catch a glimpse of this. Minutes stop counting themselves. Thoughts stretch out. Awareness floats. Time does not disappear. It just stops insisting on being measured. The universe lives in that state all the time. Expansion without urgency. Cooling without pressure. Existence without deadlines. This is why the far future of the cosmos is not terrifying when imagined properly. There is no final second, no last frame, no moment where everything suddenly is over. There is only more later, slower, quieter, thinner, even when stars are gone, even when galaxies fade beyond visibility. Time continues, softly. And that softness matters, because it means nothing is forced to end. Everything is allowed to fade at its own pace. When you place your own life inside that context, something eases. You do not need to finish everything. You do not need to resolve every thought. You do not need to reach a final understanding. The universe does not demand completion. It only allows continuation. As space cools, time stretches. As time stretches, urgency loosens. As urgency loosens, rest becomes possible. We are nearing the final stretch of this journey now. Not an ending in the usual sense. More like a settling, a point where nothing new is introduced and nothing old needs to be held onto. At first, every journey has direction, forward, deeper, closer to understanding. But eventually, direction dissolves, not because you are lost, but because there is nowhere you need to go. The universe reaches this state naturally. As it cools, contrasts fade, differences soften. The idea of toward and away loses urgency. Expansion continues, but nothing is chasing an outcome. There is motion without destination. The temperature of space reflects this perfectly. It does not point somewhere. It does not indicate progress. It simply exists as a condition. Low, even, everywhere. When you stop following a direction in thought, something similar happens inside you. The mind stops leaning forward, stops bracing, stops preparing for the next thing. Awareness spreads out instead of ahead. This is not boredom. It is release. So much effort in life comes from moving toward something, a solution, a future, a version of yourself that feels complete. But the universe does not work that way. It does not move toward completion. It moves toward balance. Balance does not require direction. It requires allowance. The cosmic background temperature is an allowance. It allows heat to leave, allows energy to spread, allows systems to relax without demand. When you let go of direction, you are not giving up. You are aligning with something older and larger than effort. Notice how your body feels when it stops leaning into the next moment. Muscles soften, breathing widens, thoughts lose their edges. This is what equilibrium feels like before it arrives. Not flat, not empty, just even. The universe will never fully reach equilibrium, but it spends eternity approaching it, always close enough to rest, never so close that nothing exists. You don't need to reach it either. You only need to feel what it's like to stop pushing in this space. There is nothing to fix, nothing to improve, nothing to understand better than you already do. The cold of space does not judge warmth for existing. It simply receives it when it is ready to go. Stories usually want something, a beginning, a reason, an ending. They pull you forward, asking for attention, asking to be followed. But not all stories are like that. Some stories reach a point where they stop asking. They don't end. They don't resolve. They simply remain. The universe is that kind of story. It does not rush toward a conclusion. It does not build toward a final message. It unfolds, cools, expands, and in doing so, becomes quieter with time. The temperature of space is part of that quieting, not a dramatic fall, not a sharp turn, just a slow easing of intensity, like a voice lowering until it blends into silence. At this point, there is nothing left to explain. You already know the facts. Space has a temperature. It comes from ancient light. It shapes stars, galaxies, and time itself. And beyond that, it shapes how it feels to exist here. When explanation fades, presence takes over. You don't need to think about photons stretching or energy diffusing. You can simply notice that nothing is pressing on you right now. The universe does not insist on being understood. It allows itself to be felt. Imagine floating, not as a body, not as an observer, but as awareness. No edges, no weight, no urgency, just the sense of being suspended inside something vast and calm. The cold of space, at this scale, is not uncomfortable. It is neutral. It does not take anything from you. It only receives what you release. Stories usually fear this moment, the moment when there is no tension left to carry them. But this story was always moving here, towards stillness. The universe does not need a climax. Its meaning is not concentrated in events. It is distributed, spread thinly across time and space, like warmth radiating outward, like light stretching into the background. You can stop listening for something to happen. Nothing is missing. If thoughts appear, let them pass. If images form, let them soften. If nothing happens at all, that is perfectly aligned with the scale of things, the background has taken over now, the same way it always does. After understanding comes quiet, not because there is nothing left to know, but because knowing has done what it needed to do. The questions loosen, the edges soften, the need to hold ideas tightly fades. This is the long quiet, the kind that doesn't arrive suddenly, the kind that settles in gently, almost without being noticed, like the universe itself. The universe learned everything it needed to know very early. Its laws were set. Its directions were clear. Expansion would continue. Temperature would fall. After that, there was no urgency, just time. We often think of silence as absence, but silence is presence without pressure. The cosmic background radiation is silent in that way. It fills everything, but it does not interrupt. It exists without asking to be acknowledged. You can forget about it for your entire life, and it will still be there. This kind of quiet is reliable. It doesn't change its mind. It doesn't accelerate. It doesn't surprise. It simply holds. As thoughts thin out, you may notice longer gaps between them. Those gaps are not empty. They are restful. Nothing needs to be solved here. Nothing needs to be named. The universe is not testing you. Cooling continues. Not because something is wrong, but because that is what space does when there is room. And there is always room. Imagine warmth leaving something slowly, not ripped away, not lost, just drifting outward, spreading until it no longer feels concentrated. This is what happens to stars, to planets, to thoughts. Eventually, even effort diffuses. Trying becomes unnecessary. Attention widens instead of focusing. The universe does not hold on to intensity. It lets intensity pass. And that is why it remains calm even after everything that has ever happened. You are allowed to be calm too. You are not required to react to every idea. You can let understanding dissolve into quiet appreciation. This is not the end. It is not even an ending. It is a state the universe passes through continuously. Understanding, then quiet, then continuation. There comes a moment when almost nothing is happening. No strong thoughts, no clear images, no need to follow anything further, just a sense of being here. The universe spends most of its existence in this state. Not empty, just unhurried. Galaxies are far apart. Stars are quiet points of light. Most of space holds only a faint glow, barely distinguishable from darkness. And that is enough. The temperature of space, so carefully measured and described, becomes almost irrelevant at this scale. Not because it disappears, but because nothing is competing with it anymore. No intense heat, no sharp contrast, just a background that gently holds everything that remains. This is what it means for the universe to be comfortable with itself. It does not need to add more. It does not need to prove anything. It allows itself to be sparse. You may notice something similar inside you now. A thinning. Not exhaustion. Not emptiness. Just less. Less urgency. Less commentary. Less movement. Nothing has been taken away. Nothing important is missing. There is simply space around what remains. The universe does not fill itself edge to edge. It leaves room, and that room is what makes it feel vast rather than crowded. Almost nothing can be very peaceful. When there is almost nothing happening, nothing can go wrong. Nothing needs attention. Nothing demands correction. This is not boredom. Boredom wants something to happen. This is contentment with what already is. The cosmic background radiation still flows. The temperature of space is still there, but they are no longer ideas to think about. They are conditions, like gravity, like time, like being held gently without noticing hands. If a thought appears, let it drift. If nothing appears, let that be fine too. The universe does not judge stillness. It spends most of its life there. We are nearing the final pieces now, not because something is ending, but because there is very little left to say that would improve this quiet. Some endings announce themselves. A final note, a closing door, a clear moment when something is finished. But the universe does not end that way. It dims. Light does not shut off. It stretches. Brightness does not disappear. It thins. Heat does not vanish. It spreads. This is the pattern written into space itself. The temperature of the universe does not collapse into cold. It drifts toward it, always moving, never arriving. As stars age, they do not scream themselves out of existence. They shine a little less. They burn a little slower. They release what they have patiently. And when they are done, what remains does not feel like absence. It feels like rest. The night sky, you know, already carries this lesson. Most of what you see is faint. Most of what exists is quieter than what draws attention. And still, the sky feels full. Dimming is not loss. It is redistribution. When something dims, it does not disappear from the universe. It becomes part of the background, part of the steady glow that holds everything else. That is what the cosmic temperature represents in the end. Not cold as punishment, not darkness as erasure, but a wide, even field where nothing needs to stand out anymore. This is why the future of the universe is not frightening when you stop expecting drama. It is not an abyss. It is a long twilight. And twilight has a softness to it. Edges blur. Sounds fade. Movement slows. There is still awareness, just without urgency. If you imagine the universe far from now, unimaginably old, unimaginably expanded, it does not feel hostile. It feels gentle, quiet, unbothered. Nothing chases anything else. Nothing competes for attention. Everything that once burned brightly has had time to rest. You do not need to hold on to brightness forever. The universe never expected that. There is a point where even dimming becomes gentle enough to stop noticing. Light is still there, but it no longer asks to be seen. Warmth still exists, but it no longer asks to be felt. Everything settles into a kind of quiet agreement. This is not the end of motion. The universe never truly stops. Expansion continues. Cooling continues. Time continues. But nothing resists it anymore. The temperature of space, once something to explain and measure, becomes simply a condition of rest. Low, even, unchanging on any scale that matters now. In this state, the universe is not striving. It is not improving. It is not declining. It is just being what it has slowly become. This is what equilibrium feels like before it is ever reached. A balance that is always approached, never forced. If you imagine drifting here, far from stars, far from galaxies, you would not feel alone. You would feel unpressured. Nothing would need your attention. Nothing would demand response. The universe does not need witnesses. And yet, it allows them for a while. You are one of those witnesses. A brief pocket of warmth, awareness, and motion inside something vast and patient. And that is not insignificant. It is rare. The universe does not resent that rarity. It accommodates it. It gives you time. As thoughts fade now, you may notice a sense of completion without an ending, like a sentence that stops because it no longer needs another word. Everything that needed to be said has already dispersed, like heat into space, like light into the background. There is nothing left to hold, nothing left to reach for, just the sense of being carried by something that has always known how to wait. At the end of everything we've talked about, there is no final fact to remember, no equation, no number, no conclusion that needs to be held in mind. There is only a feeling, a sense that the universe is not sharp or hurried, that it is not leaning forward, waiting for something to happen, that it is already doing exactly what it needs to do, cooling, expanding, resting in its own patience. The temperature of space, so cold, so vast, so quietly present, does not rush you. It never has. It will still be there whether you think about it or not, whether you are awake or asleep, whether you are watching the stars or dreaming far away from them. The universe keeps the background steady so that everything else can let go. And now, you can let go too, of the ideas, of the images, of the need to follow anything further. Nothing important will be missed. If you imagine the universe right now, do not imagine explosions or distances or scales that strain the mind. Imagine instead a wide, calm darkness, a faint, even glow, a temperature so gentle it feels like silence. Imagine that silence holding everything without effort. Your thoughts can slow, your breathing can soften. There is no task waiting on the other side of this moment. The universe does not stay awake to watch itself. It simply continues, and you are allowed to rest inside that continuation. If sleep comes, let it come. If it doesn't, that's fine too. There is no correct outcome, only the quiet certainty that nothing is wrong. The stars will keep shining while they can. The background will keep cooling. Time will keep stretching. And you, just for now, can stop. Good night. May your thoughts drift like light through expanding space. May your worries thin out like warmth fading into the cosmic background. May you rest as gently as the universe itself, slow, patient, and unhurried. The universe will be here when you wake, still cool, still calm, still waiting without asking anything at all.